Hello everyone, this is Professor Rakesh Singh Satrumem from Indian Institute of Technology, Guwahati. Title of my paper is a bidirectional pattern of DRA by employing cylindrical spoof surface plasmon Polariton structures. My co-authors are Sonu Kumar and Abhishek Maganbhai Sonagara. So here is the outline of the presentation. I will first introduce you to the topic, then we'll briefly discuss about the previous work, then we'll touch down on the proposed antenna geometry, then we'll discuss about the results obtained such as scattering parameters, gain parameters, and radiation patterns. Then we'll also discuss about what is the possible equivalent model of the proposed antenna. And finally, I will conclude the talk. So a bidirectional antenna is much desirable for applications in narrow tunnels and coal mine applications. In this paper, we propose a low-profile bidirectional antenna, which is an outcome of integration of cylindrical ring DRA and cylindrical SSOP structure. It's a well-known fact that surface plasmon Polariton is actually a similar response of SPP in the microwave frequency region. In this work, we'll excite cylindrical SSOP structures by placing in the near field of cylindrical ring DRA. The proposed antenna is designed for 2.4 to 2.5 GHz ISM band applications, and it also achieves a very low coarse polarization level. About the previous work, Fang and others have proposed a rectangular DRA for bidirectional radiation pattern applications, but then the height of the antenna is around 1 lambda. And in reference number 3, they have also proposed a cylindrical DRA for wireless LAN applications, which also has a bidirectional radiation pattern, but the height of the antenna is 0.46 lambda. So this kind of antennas has very high profile. So we want to actually reduce the profile of the antenna, height of the antenna. Our antenna will have simply around 0.1 lambda height. This is the proposed antenna geometry. We have a cylindrical ring DRA here. We're placing cylindrical SSP structure in the near field region of this cylindrical ring DRA. So we'll consider two cases when we have a single-sided SSP structure and we have a double-sided SSP structure. So both the cases will be explored in detail in this paper. As far as the material used for the antenna realization, for the cylindrical SSP structures, we have RT dioide. We have used RT dioide of thickness 0.254 millimeter, dielectric constant of 2.2, and loss tangent of 0.009. And for the cylindrical ring DRA, we have used eco-stock high K material of dielectric constant epsilon r is equal to 10, and the dimension of the cylindrical ring DRA are given by height h and diameter d naught. Both cylindrical DRA and the cylindrical SSP structures are placed over a horizontal substrate of dielectric constant 2.1 and loss tangent 0.0002. First, we have analyzed the unit cell analysis of cylindrical SSP structure. This is the cylindrical SSP structure. Unit cell is in the form of H shape. When we plot the K-beta diagram, we observe that the K-beta diagram for the proposed SSP structure is below the light line. This green line is for the light line. It is below the light line, so we have a slow wave propagation here. And it's well-known fact that if we have a slow wave propagation, we can actually do size miniaturization. So we have observed that at frequency of 2.11 gigahertz, the 40% size miniaturization is possible. In order to verify this, we have actually simulated this cylindrical SSP structure using CST Microwave Studio, and we have observed that when we have these cylindrical SSP structures with these gratings here, then we observe that there's a reduction in the resonant frequency with and without this corrugation. When we have corrugation, resonant frequency is much higher. When we have corrugation, resonant frequency is much lower than that of without the corrugation. So, and from this study, we can actually infer that we can actually make size miniaturization of almost 31%. We have observed the current distribution in such kind of cylindrical SSPB structures, and this is the current distribution. Directions are shown here, and this can be actually modeled as a dipole mode. When we have a plus charge here, minus charge here, current will flow from plus to minus charge here, and at 2.11 gigahertz, there is a lowest order dipole mode excitation in such kind of cylindrical SSPB structures. And we actually look at the cylindrical ring DRA, what kind of mode is excited in this kind of cylindrical ring DRA. And we have observed that TE01 delta mode is excited in this cylindrical ring DRA, which has a circular fit here. And we have employed the similar kind of fit which is used in reference 1. And such kind of cylindrical ring DRA with TE01 delta mode has omnidirectional radiation pattern. It can be clearly observed from this radiation pattern plot for XY plane and XZ plane here. And in the XY plane, the radiation pattern is in the form of a circle, and in the XZ plane, it is having directional patterns here. So it will give us omnidirectional radiation pattern. And the gain for this omnidirectional radiation pattern is observed to be 2.54 dBi at frequency of 2.44 gigahertz. We actually want to increase the gain also, so we'll do something else here. We'll actually place cylindrical SSVP structures one-sided and both-sided and observe that there is gain improvement. Just before that, let us try to see the reflection coefficient versus frequency of the single SSVP and double SSVP structure. When we place this single SSVP structure and double SSVP structure, there is a slight shift in the frequency which can be observed from here. This curve is for the double SSVP structure, and this curve is for the single SSVP structure. For the single SSVP structure, it is resonating around 2.4 gigahertz, but for the double SSVP structure, it's resonating around 2.48 gigahertz. We have also observed the current distribution here. This is for the single SSVP structure. This is the cylindrical ring DRA. You can see that current is flowing here in the outer loop here. Current which are induced inside these arms here, they are in opposite direction. They will cancel out, and because of this cylindrical ring DRA which is placed near in, so because of cylindrical SSV structures are placed in the near field of the cylindrical ring DRA, current distribution which is excited in the cylindrical ring DRA for the single-sided SSV structure is shown here. When we place this double-sided SSV structure, this is the current distribution which is shown here. You can see that there is a change in the direction in the current of the cylindrical SSV structure which are placed on both sides of the cylindrical ring DRA. We have observed the radiation pattern, and in the radiation pattern, you can see that now the maximum radiation is happening around 270° and 90° when we have placed single-sided SSV structures. And you can also observe the cross-polar level here. Cross-polar level here for the single-sided SSV structure is around minus 15 dB down. And gain is noted to be around 3.8 dBi. There's a slight improvement in the gain of the single-sided SSVP structure with respect to that of the omnidirectional radiation pattern we have considered in the previous case. So when we place two of them, double-sided SSVP structure at 2.48 gigahertz, we can observe that there is more improvement in the gain. Gain turns out to be around 5.42 dBi. And you can also observe that the cross-polar level has been minus 25 dB down here. We actually wanted to know the operational principle of this kind of double-sided SSV structure. So we have done some simple simulation here. We place a DRA, cylindrical ring DRA at the center, and we put cylindrical dipole in both sides of the cylindrical ring DRA, and the orientation of the current direction because of this excitation of the cylindrical ring DRA in the T01 delta mode, the current direction is dipole induced current direction is along this direction, and for this dipole it is in the opposite direction. So the total equivalent model could be this cylindrical ring DRA due to the circular flow of the current here. We can assume this is a magnetic dipole, and these two side dipoles, electric dipoles, they are in having opposite current direction. So this is the equivalent model of the proposed cylindrical ring DRA along with the double-sided SSB structures. We have observed the reflection versus frequency curve, and we have observed that dipoles only resonate at a much higher frequency. When you put DRA along with the dipoles, there is a shift in the frequency. This is much similar to what we have observed for the double-sided cylindrical SSB structure, which is placed in the near field of the cylindrical ring DRA. And the radiation pattern for the dipoles along maximum radiation is along theta is equal to 0 and theta is equal to pi. And when we actually excite the dipoles along with the cylindrical ring DRA, the radiation pattern changes. Maximum radiation is along this 270° and 90°, which is very much similar to the radiation pattern of the double-sided SSB structure, which is placed in the near field of the cylindrical ring DRA. And about the maximum gain, you can see that maximum gain is highest when we have double-sided SSB structures, and this is around 5.42 dBi, and it is much more than that of the omnidirectional radiation pattern, which was having a gain of 2.54 dBi. The maximum efficiency is around 96%. This is a comparison of our work with the reported work in the literature. The first reference is use rectangular DRA, second reference use cylindrical DRA. We actually use the hybrid of SSB structure and cylindrical ring DRA. And the peak gain, when we compare with the 1 and 2, we have better peak gain than the 2, and we have comparable gain with the reference 1. One of the major advantages of our work is that it has a very low profile. Our antenna has a height of 0.1 lambda, whereas antenna the reference 2 has a height of 0.46 lambda, and reference 1 has height of 1 lambda. So ours is a low profile antenna, which was aim and objective for designing our antenna at the beginning. So to conclude, we have proposed a low profile directional antenna, which is actually an outcome of cylindrical ring DRA and cylindrical SSB structure. And our antenna is designed for operation around 2.4 to 2.5 GHz, which is suitable for ISM band applications. We have also observed that when we place double-sided SSB structure in the near field of cylindrical ring DRA, there is an improvement in the polarization, cross-polarization level, as well as the realized gain of the antenna. These are the references. Thank you very much. If you have any question, please feel free to ask.